The standard error. How precisely does our sample mean estimate the population mean? Before we dive in, let's clarify a common source of confusion: the difference between standard deviation and standard error. The standard deviation, sigma, measures how spread out individual observations are in the population. It's a fixed property of the population and doesn't depend on sample size. The standard error, on the other hand, measures how spread out sample means are across repeated sampling. It's a property of the sampling distribution, and crucially, it decreases as the sample size gets larger. The standard error of the mean is defined as sigma divided by the square root of n. The numerator is the population's standard deviation, sigma. The denominator is the square root of the sample size. This is sometimes called the square root law. As n increases, the standard error decreases. Larger samples produce more precise estimates. Let's see this visually with the Wechsler intelligence scale, where sigma equals 15. Here's how the standard error changes as we increase the sample size. With n equals 1, the SE is just sigma itself, 15. With n equals 4, SE drops to 7.5. With n equals 16, SE is 3.75. And at n equals 100, the SE is only 1.5. Notice the diminishing returns. Quadrupling the sample size only cuts the SE in half. That's the square root law in action. Here's another way to see it. These are the sampling distributions of X bar for the Wechsler IQ scores, all centered at mu equals 100. With n equals 4, the distribution is wide, meaning sample means can be quite far from the true population mean. With n equals 16, it's noticeably narrower. And with n equals 64, it's very tightly concentrated around the true mean. The message is clear. Larger samples give more precise estimates. Let's walk through the numbers. With the Wechsler scale where sigma is 15, when n is 1, SE is simply 15, the population's standard deviation. When n is 4, SE drops to 7.5, half of the original. When n is 16, SE is 3.75, halved again. And when n is 100, SE is just 1.5, an extremely precise estimate. The pattern is clear. Quadrupling the sample size cuts the standard error in half. This is the square root law. To wrap up, the standard error equals sigma over the square root of n, and it measures the precision of our sample mean. Don't confuse it with the standard deviation, which measures individual variability. The square root law tells us that quadrupling n halves the SE, and with the SE in hand, we can describe the sampling distribution of X bar as normal with mean mu and standard deviation SE, making inference possible.